focus of this video is understanding and using the correlation formula, finding critical values and determining significance, and writing up correlational results in proper APA format. A bivariate correlation is a correlation or relationship between two variables. Each variable must be quantitative. Before attempting to use the bivariate correlation formula, ensure that you're working with two quantitative variables. Qualitative variables and constants cannot be used in the correlation formula as we will be reviewing it here. This is the bivariate correlation formula that is most typically used. It's also known as the Pearson's product moment correlation, or PPMC. Though this formula at first looks rather complicated, it's similar to a lot of the other formulas that are used in foundational statistics. That means that it's got a lot of pieces that we need to compute, but each of the pieces themselves are simple. The key here is knowing what each piece is asking us to do, and then doing those pieces or doing the steps in the proper order. Right away, I notice that n appears 3 times in the formula, and the n appears next to some information in brackets. So I need to know what n is, that's the sample size, and I'm going to be multiplying it with some other numbers I'll be computing. Next, I notice a piece that says sum x. When we do a bivariate correlation, we call one of the variables x and the other one y. Both are quantitative, and it really doesn't matter which one we call x and which one we call y, as long as we're consistent as we continue our formula. So what I'm supposed to do for sum of x is simply add all the raw scores for one of the variables. Next to that, I see sum of y, which is the same idea, but for the other variable. I'm just going to add all the raw scores for the second variable, which we call y. You might also notice that the sum of x and the sum of y are next to each other in brackets. That means after I find those two, I will be multiplying them. I also notice here that the sum of x appears on the bottom of the formula, as does the sum of y. So both the sum of x and the sum of y will be put into the formula twice. Now let's move on to the sum of x's which have been squared. Following order of operations, I would first square each raw score for x, then I would sum them up. Notice that this piece and the piece next to it look really similar, but for sum of x's which have been squared, the squaring is inside the brackets, which means we're going to square first, then add. Where the one next to it is the square of x's which have been summed, which says we're going to add first before squaring. So be very careful about these two. These numbers are going to generally be different. Next up, we have the sum of y's which have been squared. Similar to the sum of x's which have been squared, this time we're going to square each y variable and then sum them up. And the last piece of our formula is the sum of x times y. Following order of operations, we would multiply each x score by its corresponding y score, and then we would add them. Notice that this is not the same as summing x's, summing y's, and then multiplying. In this version, we're doing the multiplication first, then the adding, whereas in the two pieces next to it, we'd be doing the adding first and then the multiplying. So before we can find the correlation coefficient, also known as R, we need to find each of these 6 pieces and then plug them into our formula. Let's assume that I hypothesize that the longer plants are exposed to direct sunlight, the more they will grow. Now notice here that time is quantitative because we're talking about longer spans of time, and we're also looking at growth quantitatively because we're talking about more growth versus less, so we're quantifying here. In this example, our hypothesis is that the R for this x and this y will be greater than 0 because we're saying that there would be a positive relationship here. That's because more time in the sun is expected to be related to more growth. We aren't simply saying that the time spent in the sun and growth will be related. We're saying that they will be positively related because we're saying more of x is going to connect with more of y. That also means less of x will connect with less of y. So if we think there will be a positive correlation, we use what's known as a one-tailed test. Specifically, we're expecting that if we gather our data and create a scatter dot graph, that we'll see a line that's generally pointing up from left to right. A graph like this has a positive slope, so we call this a positive correlation or a positive relationship between the x and y variables. So here's our hypothesis written in standard sentence format, and here it is in symbol format. Suppose we collect data on 5 plants. For x, I will use hours of sunlight. For y, I will use inches of growth. Suppose we had a plant exposed to sunlight for 2 hours, but grew 0 inches in a 24-hour period. Another plant was exposed to 3 hours and grew 1 inch in a 24-hour period. A third plant got 4 hours of sunlight and also grew 1 inch. Another plant got 5 hours of sunlight and grew 2 inches. And a last plant got 6 hours of sunlight and also grew 2 inches in that time period. So now I have my x data and my y data for each of the 5 plants. It's very important that we keep these data together so the x and y's for each person or each plant in this case stay on the same line together. Because if we were to scramble those up, we would end up with a result that is incorrect. Now we're ready to find the 6 pieces for our formula. We already know that the sample size is 5. Keep in mind the sample size is 5, not 10, because each individual plant has an x score and a y score. So each row represents a different plant. Next, we can find the sum of x and then the sum of y. To get the sum of x, I simply add all the raw scores, and I'm getting a sum of x of 20. I repeat this by adding all of the y values, for which I find a sum of 6. Next, we'll find the sum of x's which have been squared. So I'm going to take each of my x values and I will square it. I recommend using this table format to help you keep your data organized because we've got a lot of steps and you want to keep track of each of them. Once I've squared my x's, I'm going to sum them up to get the sum of x's which have been squared. That means I squared them first, then added them. And when I do that, I'm getting the sum of x's which have been squared is equal to 90. I'll repeat this to get the sum of y which has been squared. I'll square each of my y scores, then I'll sum them, and I get a sum of y's which have been squared of 10. The last piece I need to find is the sum of x's times y's. This means I have to multiply each x by its y and then sum. I like to create another column on the end that helps me keep these organized as well. Next, I'll multiply each x by its y. 2 times 0 gives me the product of 0. The product of 3 and 1 is 1. The product of 4 and 1 is 4. The product of 5 and 2 is 10. And the product of 6 and 2 is 12. I'll add these products up to get the sum of x times y, which gives me 29. So my sum of x's times y's is 29, keeping in mind that I do the multiplication first and the summing second. Now I have all of the pieces I need for me to calculate my correlation coefficient. Now that I have all my pieces, I no longer need to look at the way I computed those, that I can focus on simply plugging these into the formula. Let's start plugging in with the numerator. My sample size was 5, and my sum of x times y's, x's times y's, was 29. From that, I'm going to subtract the product of the sum of x, which was 20, and the sum of y, which was 6. Now we're ready to look at our denominator. I've already put my square root sign, so I'm going to put that sample size in again. That's going to get multiplied by the sum of x's, which had been squared, from which I will subtract the sum of x's, which are going to be squared. That's going to go inside brackets because that's one piece altogether. Then we repeat that same structure, but this time for y, putting in sample size, multiplying that by the sum of y's which have been squared, and subtracting from that the sum of y which we're going to square. Let's start by finding 5 times 29, which is 145. Then I'm going to subtract from that the product of 20 times 6, which is 120. Now I'm ready to move on to my denominator. Next, I'll find 5 times 90, which is 450. And I'll subtract from that 20 squared, which is 400. Onto the y side, I'll do 5 times 10, which gives me 50. And I'll subtract from that 6 squared, which is 36. Already we can see that our formula is looking a lot simpler. So let's tackle that numerator. 145 minus 120 gives me 25. And now I can move on to the denominator, starting with 450 minus 400, which gives me 50. And then I'll do 50 minus 36, which gives me 14. Next, we'll multiply the two parts of the denominator. 50 times 14 gives me 700, which I now must square root. So now I have r equals 25 over the root of 700, which gives me 26.45751. I'm going to keep all 5 of those so I don't have rounding error at the end. So now I simply divide 25 by 26.45751, and I get 0.94491. We want to round it to the hundredths place, so our rounded final answer is 0.94. This is a very strong positive correlation. That means there's a really clear connection between hours of sunlight and growth. Let's take a look at this visually by creating a graph. Let's use those data to plot them on a scatter plot. That's a two-dimensional x by y graph. This will allow us to see visually that very strong positive correlation. The coordinate for the first score is over 2 up 0, so they're on the x-axis. The second person is over 3 up 1, so they're here. The next person is over 4 up 1, so they're here. The next person is over 5 up 2, and the last person is over 6 up 2. Once I've noted all the dots, I can see an upward trend here, a fairly clear positive trend among my dots. Though my dots are not perfectly in a straight line, we're pretty close. Look at the vertical gaps between the dots and the line. This is how incorrect my line is for each of the dots. These gaps are known as residuals. Residuals are vertical gaps between the dots and the line. We can also think of these as error. In fact, if you learn about regression, you'll learn that we talk about residuals as errors in the line when the line is used to find the dots. Our residuals here are really small. These are really tiny gaps between the dot and the line. When your dots are close to the line, and thus residuals are small, you have a strong correlation. But when the gaps between the dots and the line are large, you then have lots of residuals or error, and that's an indicator of a weaker correlation. We had a correlation of 0.94. This is very strong, and you can see that the line is clear. We see that upward slope indicating that it is positive, and the gaps or residuals from the dot to the line are very small. So here we have visually the representation of a very strong correlation, and here we have numerically as a summary a representation of a very strong positive correlation. Once we have the obtained value for any inferential test, our next question is this result significant? We had a result of r equals 0.94. Now because this is about as high as you can get, because the highest you can get is a 1.0 or a negative 1.0, I'm guessing that this is going to be significant. But to really determine it, I need to compare this result to a critical value. To find your critical value, you must first determine whether you are using a one-tailed test or a two-tailed test. Recall that our hypothesis was that more sunlight would relate to more growth. That's a positive correlation that was hypothesized, so we would be using a one-tailed test because we've given the direction that we expect things to go. We're not looking to see if our result is a positive or a negative correlation. We're specifically looking at only one thing, and that's whether our result was strong enough and positive. Our result is positive, so that's a pretty good indicator that we're on the right track. The next thing we need to know is our degrees of freedom. The degrees of freedom for a correlation are equal to sample size minus the number of variables being computed. So the degrees of freedom for a bivariate correlation is always sample size minus 2. Our sample size was 5, so our DF is 5 minus 2, which is equal to 3. So I see that my critical value when I'm using alpha equals 0.05 is 0.805. Don't forget, we use alpha equals 0.05 in the behavioral and social sciences unless otherwise specified. That means a 5% chance of a type 1 error, and that's the most we're willing to take. So now that I've found my critical value is 0.805, I compare it to my obtained value of 0.94. If the obtained value is greater than the critical value in absolute value, our result is significant. So in this case, our result is significant because we've beat the critical value. The last thing for a researcher to do is write their results in APA format. When we write results in APA format, we always start by stating the test used and the hypothesis, followed by the main results and any detailed results that go along with our test. So far we've done the first two parts, so we can summarize those sentences before turning to the third. I'll start by stating my test used, which was a bivariate correlation, and my hypothesis. So I'll write, a bivariate correlation was used to test the hypothesis that hours of sunlight would positively relate to growth. My second sentence gives the main result and supports it with evidence in proper format. There's a couple of ways I could write this sentence, one of which is, this hypothesis was supported by a very strong, significant, positive correlation. R of df3 equals 0.94, p less than 0.05. I could have also said there was a significant, very strong positive correlation between sunlight and growth, and given the results. Or I could have said this was significantly reported by a strong positive relationship between sunlight and growth, and given the evidence. So as long as all the key pieces are there, there's a couple different ways we can word this sentence. That leaves just one piece for us to get to. The details. Many inferential tests have extra details that we can compute after we found a significant result. For correlation, that extra detail that we can give is called the coefficient of determination. The formula for the coefficient of determination is r squared. This is why we do it after we have found that r is significant, because we can't assess it until we know what r is. The coefficient of determination indicates how much of the variability or variation in x is accounted for by variability or variance in y. This is basically a fancy way of saying, as a percentage, how connected are x and y. The stronger the correlation, the more connection there is. And the weaker the correlation, the less connection there is. Essentially, the coefficient of determination is saying, what percentage of y do I know based on x, or what percentage of x do I know based on y? We typically talk about understanding y using x because that becomes the foundation of something called regression. But you can actually talk about x accounting for y or y accounting for x. I'll start by using our rounded answer here. We had a correlation coefficient, or r, equal to 0.94. If you square this, you get 0.8836. As a percentage, that's 88.36%. So if we use our rounded answer, we would state that 88.36% of the variability in x is accounted for by variability in y. But it is preferable that we use an unrounded answer to square. That way we won't introduce too much rounding error. In that case, I'm going to go back to my calculator and I'll see that my r before I rounded it was 0.944911. When I squared that, I got 0.892857. If I round that to the hundredths place as a percentage, I get 89.29%. This is the preferable answer because it's more accurate. So this would indicate that if I know about x, then I know about 89.29% of what's going on with y. This is known as the coefficient of determination. That's how much of y is known using x. This means that the remaining amount leading up to 100 is unknown. This is known as the coefficient of alienation. To be alien means to be foreign or unknown. So our coefficient of alienation tells us what's left unknown about y when we've used x. The formula for the coefficient of alienation is 1 minus r squared. The alienation for this is 1 minus 0.892857, which gives me 0.107143. As a percentage, that's 10.71%. We want to round to the hundreds place. That's left unknown. So what this is telling me is that x and y are so connected that x tells me about 90% of what's going on with y and only leaves about 10 to 11% of that unknown. The coefficient of determination is reported in the APA formatted write-up when the correlation is significant. The alienation is not typically reported for correlation, but it does give us an indication that there's more out there for us to explore if we want to understand 100% of what's going on with our y variable. When r is significant, r squared is reported and interpreted as part of the APA formatted write-up. It'll be the last sentence of our paragraph. However, if r is not significant, it means that x and y don't show any clear connection, and thus there's no reason to report the r squared. So when your r value is not significant, and thus your hypothesis is not supported, you don't have a third sentence to report in APA. We only use this third sentence when we had a significant result for r. Because our coefficient of determination was 89.29%, I'll add, therefore, approximately 89.29% of the variance in growth, which is my y variable, is accounted for by variance in sunlight, which is my x variable. Now, this is kind of a strangely worded sentence if you're new to statistics, but what we're essentially saying here is that this is the percentage of y which is known using x. So there you have it. That is the correlation formula, how to determine significance, and how to do a full write-up for a significant result in APA format.